Today's lesson is going to be over periodic trends, but to explain periodic trends in AP chemistry, they are often going to ask you to answer a question based on something called Coulomb's law. And so I want to go through what Coulomb's law is, and then we'll get into the trends, which you have to memorize what the pattern is. And we've seen almost all the trends in our high school level chemistry. There's only one that should be completely new to you for AP Chem. So Coulomb's law is a math equation. And in this math equation, we can use it to express what is going to happen to the forces within an atom if we change any sort of characteristics of those forces. So a lot of times we'll have questions that will start out by saying, according to Coulomb's law. We're going to use Coulomb's law, which is a math equation. I'll talk a little bit about the difference between these two and why we write it in different ways. And what it does, it explains how changing the distance or changing the charge of a particle affects the attractive forces of an atom. So these Q1, Q2 are going to be your charges of your atoms within a chemical compound. So we're saying what would happen if we changed our charges from +1, -1 to maybe +2, -1. So we're saying that Q1, Q2 is going to be the charge of the particles within that chemical bond. And then R is going to be my distance that occurs when they chemically bond to each other. And we'll talk more about this here in a minute when we get to the atomic radius. I'll talk more about what this represents with your R squared. So in this equation, it's going to often be given to you like the format over on the right in AP Chem, because your Coulomb's law is actually a math equation. It's actually going to be a math equation where we have forces equal to, but we're missing a part of it. So AP says that it's proportional versus equal. And so let me fill in the rest of this little equation over here, because I didn't put in the line, because when I underline things that have subscripts, it marks through them and makes it really hard to see. So in this equation, what I'm missing is there actually should be a K right here, and that K is Coulomb's constant. So you can calculate the force. It is a math equation. We can know Q1, Q2, and my distance between the atoms, and I can go back and calculate force. Or if I know force, I can calculate any of these variables within the equation as long as I know what that K is, which is Coulomb's constant. But the thing with AP Chem is they never ever ask us to actually calculate this equation. They ask us to use this equation to represent what would happen if. So if we look at this last thing, this sort of summarizes everything together down here. It says, in simple terms, the higher the charge of the particle, the greater force they exert on one another, and the greater the distance, the less force the particles exert. So let's talk about how we can describe this mathematically. For some of you guys, you are great at describing your answers in words and using words to explain yourself clearly. I'm not. I'm really good at using math to prove a concept, and most of you guys are going to be like that as well. If you're math-minded, words are not always our friends. We don't always know how to express ourselves using those words. So I'm going to teach you guys how we can use this equation to represent what this sentence states. So if it's saying that if I increase this charge, so like if I go from +1 to -1 to +2, -1, if I increase my charges, because of the way this math equation is set up, if I increase this number on top, let's say initially it was 1 and then I increase it to 2, well, just the way that math works, I'm also going to increase my force. So if I increase my charges, this is a direct relationship, and if I increase my charges, then my force also increase. The same is true for the opposite of that. If I decrease my charges, I decrease the force. Because again, this value is a direct relationship to this. As I change these values, it is going to directly be proportionate to this. This, and it is inversely proportionate to my force because it is on the bottom of this equation. So if I increase this, let's say that this number was 1 and this number was 1, then my force would be equal to 1. But if I change this so that I've doubled my distance between the two atoms that are bonding, and now it is 1 over 2, I did not increase my force. I am actually decreasing my force because it is inversely proportionate. So whatever I do here has the opposite effect on my force. So if I increase the distance between, the greater the distance, the less the force of particles can attract on each other. And so I'm going to teach you also how to use this math equation to, instead of having to say according to Coulomb's law, I can just say if I increase this, I decrease this, or I can use and explain myself in words like they did on this example. So let's look at what these periodic trends are so we can go back and use this Coulomb's law a little bit more. So in this picture, it is giving you a visual representation of what's happening in an atom. So in an atom, you have your nucleus, and your nucleus has your protons, and they're positively charged. Your electrons orbit outside of the nucleus. They're attracted in because of the positive-negative attraction within the atom. So, according to Coulomb's law, because of this math equation, if I increase this distance, the r squared, because it's inversely proportional, I'm actually going to decrease the force. It's going to take less energy. So it is easier to take away that electron because it's further away than it is to take either of these electrons because they are closer to the nucleus. Because I increased my distance, so I decreased my force, because if I increase this one, I decrease that one. Okay, so I can say it in this way. According to Coulomb's law, less energy is required to move the electron in the second energy level than the electron in the first energy level because the larger radius results in a lower force of attraction. Or I literally can take this equation and I can say if I increase this, I decrease that. I can use this math equation to represent what I'm meaning, or I can write myself out in sentences if we're really comfortable with describing ourselves in words. So again, here's an example of a question you might see on AP in an FRQ. It says, look at the diagram below. Which electron A, B, or C is easiest to remove? Justify your choice in terms of Coulomb's law. So here's the deal. AP asks you all the time. They'll ask you a question, then they say justify. So just answering the first part of the question will not get you full points on the AP exam. You also must justify by explaining yourself either using math explanations or by describing with words. So in this one, if we look at these three different things, in atom A, I have a positive 2 charge for my nucleus, and I have an electron outside of it, something that's got a negative charge. So this would be like magnesium and chlorine, if we were talking about two different elements bonding to each other. Or if I was talking about just within an atom, then this could be like helium, because helium has a positive 2, but helium with only 1 electron. So it really can be used to describe either situation. AP is just saying which one of these is going to be the easiest to remove because we don't know exactly what's happening in this example. In this one, I have positive 2, negative 1. This one I have positive 1, negative 1. And then this one I have positive 1, negative 1. So these two scenarios have the same charges, but they do not have the same distance. So in that equation, those Q's are the same, for example B and example C, but the R squared is not the same. So this one says electron C is the easiest to remove. According to Coulomb's law, the force of attraction is proportional to the magnitude of the particles' charges and inversely proportional to the distance between them. That literally just described this equation, is all that it just described. Picture C has the lowest magnitude of charges, positive 1, negative 1. So it says 1 positive and 1 electron. Again, we aren't really sure what the situation is. And the largest distance between charged particles. As a result, the electron in C will be less attracted to the positive charge. So again, I've increased my distance. So I've decreased the force of attraction, which makes sense. If you think about these as magnets, if these two magnets were very close to each other and I had two opposite poles of magnets, they would be very attracted to each other. The further I pull those magnets apart, the less I feel that force of attraction. It's the same thing in an atom. So what are these periodic trends? Well, there's 4 that you're going to be responsible for knowing, and a new one that comes up occasionally in AP. They ask us to know about it, but we rarely have questions about it. So all the trends relate back to the concept of atomic radius. So atomic radius is the size of the atom. If I go back to this slide, I'm talking about this atom right here. So the size of the atom. How many rings does it have around the nucleus? Again, Bohr's model is a great model to use to think about this because most people's minds do not think in quantum mechanical model, but you can visualize Bohr's model. So in this atom, there's a nucleus and then there's 2 energy levels. So this electron is further out here. This example is lithium because it has 3 total protons and 3 total electrons. The atomic radius is how many rings are around that nucleus, how many energy levels are there is going to make the size of the atom. This is measured in either nanometers or picometers because atoms are super teeny tiny. So we're talking about very small distance measurements. And the general trend, and this is what I want you really to start memorizing and remembering from your high school level chemistry. So we memorize the trends as up and over, so up a group across a period. And the reason we do this is because it has the same trend if we memorize it that way. So as I move up a group, the atomic radius decreases. Well, that makes sense because if I'm looking at group 1, my francium has 7 energy levels, but my hydrogen only has 1 energy level. So if we think about in terms of Bohr's model, like this picture, 1 ring is going to make the atom much smaller than 7 rings that francium has. As you move across, the trend is also going to be to decrease. Now, this part is a little bit more complicated, and it is because we increase that nuclear charge. It's called having a higher effective nuclear charge. As I move across a period, so if I'm looking at period 3, sodium has an atomic number of 11, magnesium 12, aluminum 13, so on and so forth. As you add 1 more proton and electron, it's like you're making 2 magnets get stronger, and that force of attraction is going to become greater and actually shrinks the atom slightly. So on my periodic table, if I'm talking about just the sp and d orbitals, not worrying about the f block because, again, it's really doesn't have a lot of chemical bonding. We don't talk about a lot of those elements. And then francium has the least or the largest atomic radius, whereas helium, which is at the very top, would have the smallest atomic radius because of this trend of decrease up, decrease across. When we're talking about chemical bonding and Coulomb's law, we are going to be looking back at this atomic radius. This has a huge play in the attractive forces between 2 atoms. If I had lithium, which is a pretty small group 1 metal, and fluorine, which is another pretty small group 17 non-metal, if I bonded those 2 together, they're going to have a super high force of attraction because they're both very small, because lithium has a very small atomic radius over here, and fluorine has a very small atomic radius over here. But if I took francium, which is at the very bottom of this periodic table of this group, which it usually doesn't bond because it's so radioactive that it decays really fast. But if I took francium and I bonded it up here to fluorine, it would not have as much of an attractive force because there would be a very large amount of space around francium than there would be around fluorine. And so what happens there is we decrease that force of attraction because of the size of the atom. And so that's where Coulomb's law comes in, is if I go back over here, if I'm comparing these values, if I increase that distance, I decrease that force. And that makes sense because the further away the nucleus is from the other element's electrons, the less attractive force there is. Ionization energy is the second trend you need to be familiar with, and it is the energy to become an ion. That's really the definition of it. So an ion is something that is a charged particle. It has lost or gained electrons. And so in order to lose or gain electrons, it goes from being a neutral atom to an ion. So ionization energy is how much energy is it to remove 1 electron from a neutral atom. This trend is opposite. This trend is going to be increase, increase, is going to increase up, increase across. Because the thing that's going to affect these is the size of the atom. The smaller the atom is, the harder it is going to be to pull that electron away from it. So if I go up to helium, helium's 2 electrons are right next to its nucleus. So the trend is increase up, increase across. Because helium is the smallest atom on the periodic table, it is the hardest to take the electron away. It's going to take the most energy to break that attractive force from the electron to the nucleus. Whereas over here with francium, francium has 7 energy rings. It has 1 valence electron. So that one lonely electron that is all the way out in the 7th ring of francium is going to be pretty easy to remove. So going back to this picture, think about this picture. This electron is easier to move than this electron. So if francium had 7 rings, it's going to be easier to remove that electron away because it's farther from the nucleus. So your atomic radius determines the ionization energy. So this trend is opposite. It's increase up, increase across, but it is due to the atomic radius. Now, most elements do not lose just 1 electron. Most elements, in order to become stable and to get to that electron configuration of a noble gas, they will have to lose more than 1 electron. So like aluminum has 3 valence electrons, it needs to lose 3 to become stable. But whenever I keep losing electrons, it still takes more energy for the removal of other electrons, even if that element wants to lose those electrons. And the reason is because of this weird nuclear charge, where the more I take away my negatives, then that positive charge doesn't change, because the nucleus of the atom is the identity of the element, and in chemical bonding, the amount of protons does not change in that atom. We are just moving these out and making the positive and negative charges no longer be equal. If I take away this electron, I now have a positive 3 and a negative 2. Because of that, I have increased what we call the effective nuclear charge. So that nuclear charge minus electron shielding. And what electron shielding is it hides the nucleus away, because the attraction of those electrons next to the nucleus to the itself, and then those other electrons further out aren't noticed as much. So if we look back at this again, these 2 electrons are super attracted. This one is not as attracted because these are shielding that electron from the attraction of the nucleus. So here's a couple questions. Which has a higher first ionization energy, lithium or sodium? Well, we look on the periodic table and then we just think about the trend. Lithium and sodium are both in the first group, the up and down group. And so we are looking at that group trend, and the group trend is it increases as it goes up. And so the one that is going to have a higher ionization energy is going to be lithium. And the reason why is because the atom is smaller and the electrons are going to be more attracted to that nucleus. For the second one, which has a higher first ionization energy, sodium or aluminum. Well, sodium and aluminum are in the same period. So then we're going to look at that period trend, which is increase across. And so out of those 2, aluminum is going to have a higher first ionization energy. And the reason is because aluminum has a smaller atomic radius, which is going to make the electron be more attracted to the nucleus. You can also describe the trends. AP is almost never going to ask you about the why, but they will sometimes ask you to describe it in terms of Coulomb's law. And so if I'm doing that, then whenever I have a smaller radius, so if I have a smaller radius, I make my radius smaller, then I can come over here and it will increase my force. So again, you can use this to describe the math relationship. So if I make a smaller radius, I increase the force. This one has a smaller radius, so I increased the force. This one has a smaller radius, so I increased the force. The next trend is ionic radius, and this is going to be what happens to the size of the atom when it loses or gains electrons and becomes an ion. So we're trying to figure out what is the size of the ion. So an anion, and you really need to stick these words in your head because we use this all year long to describe relationships within an atom. An anion is a negatively charged ion. It gains electrons. Most of your polyatomic ions are anions, and then your nonmetals on the periodic table are anions. Cation is a positively charged ion. Your cations are your metals, or ammonium is your other cation. An anion has gained electrons because in an atom you have an equal number of protons and electrons. If it's neutral, in order for it to come overall negative, that means it has to have more electrons than it does protons, because the number of protons does not change because that's the identity of the element. And so it has gained electrons to become negatively charged. To become positively charged, it has lost electrons. Your ionic radius is also measured in those nanometers, those super teeny tiny distance measurements. And for your size of the atom, anions get bigger, cations get smaller. So anions get bigger because if I gain electrons, what happens is electrons are all in the rings, and you need to have a certain number of electrons for certain elements to become stable, to be like the noble gases for their electron configuration. But when you put a bunch of negatives next to each other, then there's going to be what we call electron-electron repulsion. Even if that atom is becoming more stable, there is still electron-electron repulsion, and it makes the size of the atom get bigger. Cations are going to get smaller. So I can use an example back here that we looked at. So if I lose this electron right here, this is going to become, this is lithium. It becomes then my lithium +1 ion because it loses that electron. When it loses that electron, it also loses that entire energy level because it's no longer occupied. So then it only has that first energy level. So it becomes a smaller radius whenever a cation becomes, when an atom becomes a cation, it is going to lose those electrons. And on top of that, because of the amount of protons and electrons, there's fewer electrons to have that electron-electron repulsion. The last trend, this is the trend that you shouldn't have talked about. In your high school level chemistry, you should have talked about ionic radius, you should have talked about ionization energy, you should have talked about atomic radius, and then you probably haven't talked about electron affinity. And so with electron affinity, the problem there is that the amount of energy, by definition, it's the amount of energy involved when an electron is accepted by a gaseous atom to form a negative ion. This is also the likelihood of a neutral atom to gain an electron. So on our periodic table, the things that want to gain electrons are going to be our nonmetals over on the right side. So this trend is also going to be increase up, increase across, because these things over here want to gain electrons. These things over here really don't care about gaining electrons, but the trend still has increase. So let's look at one example of a question that you would possibly see on the AP exam over this topic. And we're going to talk about the last trend in this question, and we're going to go over the very last trend, which is electronegativity. So the trend of electronegativity is going to be what is the likelihood of an element to chemically bond is really where electronegativity comes in. What is the likelihood of accepting that electron? And so this trend is going to also be the same as ionization energy, is going to be increase up, increase across. Now, for electronegativity, it is about chemical bonding purely. The other ones are just about characteristics of an atom, but this one is about chemical bonding. So in this one, we sort of ignore that last column. We ignore those noble gases. We won't talk about them in this trend. because they typically don't chemically bond unless we force them to, and then there's only a few of them that will do that, and I'll talk about that another day. So this trend is increase up, increase across. It says, which of the following best explains why the electronegativity of chlorine is less than that of fluorine? So anytime you have these questions that are talking about electronegativity, you are looking for two answers. Number one is if it is talking about Coulomb's law, if it is asking you to describe it somehow within this relationship here. And again, it is all based on either the charges or the radius of which thing is going to more likely increase that force of attraction. Or if it doesn't mention anything about Coulomb's law, then the thing that you're going to be looking at is the size of the atom, because that's really what it relates back to, which is what Coulomb's law is representing by that R squared. And so when I'm looking at those answers, that's what I'm trying to figure out. Anytime it talks about mass, that is not what causes trends. Trends are caused by sizes of atoms, not the mass of the atom. So never let that trip you up. Mass of the atom almost never has any bearing on any of the trends and characteristics we talk about throughout the year. This one is saying chlorine has more protons than fluorine, which is a true statement. Sometimes there are going to be true statements, but they don't match whatever this characteristic is. AP will give a true statement, but it doesn't matter to this one. So that is a true statement because chlorine has an atomic number of 17. Fluorine only has an atomic number of 9. This one says when chlorine and fluorine form bonds with other atoms, the chlorine electrons are more shielded from the positive chlorine nucleus than the fluorine bonding electrons are shielded from the positive fluorine nucleus, which that's also going to be a true statement. But that, again, doesn't have any bearing in this concept because it's saying why is chlorine bigger than fluorine, or less than the size? Why is chlorine a larger size than fluorine, or why is chlorine's electronegativity smaller than fluorine? And so then the last one, because chlorine is larger than fluorine, the repulsions among electrons in the valence shell of chlorine are less than the repulsions among the electrons in the valence shell of fluorine. And so this is going to be the correct answer in this one because, again, the size of the atom is what it's playing into here, because the larger the atom is, the more they're going to be able to avoid those repulsions. So this topic, you want to go through and stick these trends in your head about these different characteristics. It all goes back to Coulomb's law. And the trend that comes back up quite a bit in the next few sections is going to be this trend of electronegativity, because electronegativity directly tells us how something is going to chemically bond. But the next best trend to always remember is the atomic radius, because that's going to be the one that we want to make sure that we understand. The size of that radius is what has the biggest effect for us on this concept of Coulomb's law.